by definition, an eigenvalue-eigenvector pair is a constant and a vector, a lambda and an x, for which a times x is equal to lambda times x, right? So coming back to some of the examples that we just looked at in our original transformation, 1, 2, 2, 1, we found that there was a direction, the direction of the vector 1, 1, where the image a times that vector is just parallel to the original vector. So when I took 1, 1 and I transformed it, what I ended up getting is 3, 3, right? Which happens to be 3 times 1, 1. And so we would say that 3 and 1, 1 together form an eigenvalue-eigenvector pair. So 1, 1 is the eigenvector, 3 is the eigenvalue. And then when we went to do the same thing with the anti-parallel stretch direction, which is what gave us the explanation for why the transformed cat is actually a mirror image of the original cat, right? The spot moved to the other side of its chin. That we found that w, the vector 1 minus 1, is an example of a vector that's getting anti-parallel stretched by this. And for that reason, its image is equal to -1 times itself. And so -1 would be another eigenvalue for this matrix, and the vector 2 minus 2 would be an eigenvector associated with the eigenvalue, -1, right? So there's this hand-in-glove quality. If you tell me the eigenvalue, that's associated with a particular eigenvector and vice versa. So you have to maintain the connection between those two things. Don't let them get separated, because then you're not going to be keeping everything organized in the way that we want to. So we call that lambda and that x an eigenvalue-eigenvector pair if they are a solution to a times x equals lambda times x, where lambda is a constant and x is a non-zero vector. And so our job for the rest of today is just to develop the techniques for algebraically finding the values of lambda and x, the eigenvalues and the eigenvectors. And so it ends up being a two-step process by which we first start by trying to find eigenvalues. We try to find the lambdas first. And then once we know what the eigenvalues are, we can then use those eigenvalues, plug them into this equation, and then solve this equation for x using the ordinary tools of linear algebra solution solving that we have from the first week of the semester. And so it's finding the eigenvalues that is the interesting part of this. It's the part that we shouldn't be expected to know how to do just yet. But if you feed me a lambda, then we should be able to find out the solutions x just using ordinary, reduced row echelon form techniques. So our first question is, how do we find those eigenvalues? How do we find eigenvalues for a square matrix? To solve the equation ax equals lambda x, what we want to do is just rearrange the equation so that it looks like matrix times vector equals vector, because those are the kinds of equations we know how to solve based on what we did in the first week of the course. So doing that just requires us to subtract the lambda x from both sides. Right? So when a times x is equal to lambda times x, then we also know that ax minus lambda x is equal to the zero vector. Right? But this still doesn't look like matrix times vector equals vector, because on the left-hand side I have matrix vector minus matrix vector. So I'm going to factor out this vector x from the left-hand side of this equation. If I factor it out from the first term, I just get a, naturally. But if I factor it out from the second term, I need a matrix in here to be multiplying by the vector x. And since I don't have a matrix in there, I'm just going to wedge in the identity matrix in its place. And so the equation that we end up solving using our techniques from the very beginning of the course is the equation a minus lambda times the identity matrix times x is equal to the zero vector. So this is an ordinary matrix vector equation. It's just that the matrix that we study is not A, but it's A minus some multiple of the identity matrix. And if we choose that multiple of the identity matrix wisely, we're going to be able to get, and then here's where I'm going to underline this word, non-zero solutions to this equation. But in order to get non-zero solutions to this equation, we have to figure out what that tells me about the matrix A minus lambda I. And so this is your job with your team for about the next 5 minutes or so. Figure out which of choices A through D are going to need to be true in order for this equation to have a vector x which is non-zero that solves this equation. So it's that non-zero piece that is the critical piece in this process. what we need to be the case, in order to have a non-zero solution of this matrix equation, we need for the solution set, right, needs to contain a non-zero vector. But the solution set of this equation is nothing more than the kernel of the matrix A minus lambda I. So the kernel of A minus lambda I must contain a non-trivial vector, right? The non-zero vector. And if the kernel of a linear transformation contains a non-zero vector, that means the nullity. I'm adding a couple of extra steps in here because I think they're going to help for us to make the case. The nullity of this matrix must be what? If there's definitely a non-zero vector in this kernel, what can we say about the nullity, the dimension of the kernel? And if the nullity of my linear transformation is 1 or more, what does that tell me about solutions to the equation, solutions to the homogeneous equation? A minus lambda I x equals 0 are
not unique.
Not unique. Yeah, very good. Solutions to the homogeneous equation are not unique. And what does that tell me about the invertibility or not of the matrix A minus lambda I?
It is not invertible.
There we go. Is not invertible. So that's option B.
Yeah.
Yep,
Okay.
option B. So this is the algebraic test for us to figure out how to find an eigenvalue for a matrix. We just want to find a lambda for which A minus lambda times the identity matrix is not invertible. If I can find such a thing, then we are going to have found an eigenvalue for our matrix. So then, of course, the obvious question is, how do we find such a lambda? Like, how can we use linear algebra to find for which lambda we have this happen? And this is the magic of determinants. So remember, when we first introduced determinants, we said that determinants give us a test, a criterion for invertibility for a square matrix. A matrix is invertible exactly when its determinant is not 0. So a matrix fails to be invertible, which is actually what we want this time. A matrix fails to be invertible when its determinant is equal to 0. And so if I take the determinant of A minus lambda times the identity and I get 0 as my determinant, then I know that my lambda is going to be an eigenvalue of my matrix. Right? And so this is why we end up finding eigenvalues first, is because this determinant criterion doesn't give us any information about the solutions other than that the solutions to the homogeneous equation are not unique. It just doesn't tell us what the solutions are. It tells us that they're not unique. And so this equation, determinant of A minus lambda times the identity is equal to 0, is called the characteristic equation for the matrix A. And the polynomial, which is on the left-hand side, and here comes our polynomial, so this is the reason that we refreshed our memory on things like the quadratic equation coming into this week, that this left-hand side of this equation is just going to be a polynomial whose variable is lambda, right? Whose variable is the unknown, the heretofore unknown eigenvalue. So let's just pause for a second and see if we can reconstruct the eigenvalues and the eigenvectors of the original matrix that we were looking at, our cat map 1, 2, 2, 1, that we started with at the beginning of this exploration. What I want to do is have us jump forward into what I call the preview activity for the last section of what we're doing. And so what I'll ask you to do here is to determine the characteristic polynomial of the matrix 1, 2, 2, 1. So what do I mean by determine the characteristic polynomial? I'm going to zoom in on this a little bit and just say a few more words about that before I turn you loose on it. What we're doing when we're trying to find the characteristic polynomial of a matrix is we are just trying to take the determinant of that matrix minus lambda times the identity. And so the first thing that we do is we just have to compute what is A minus lambda times the identity. And so if I take 1, 2, 2, 1 as my matrix, and I subtract lambda times the identity matrix, remember the identity matrix is 1, 0, 0, 1, right, for the 2 by 2 case. So when I subtract lambda times that much, what ends up happening is that I subtract lambdas everywhere on my main diagonal. Right? And then I take the determinant of that matrix with the lambdas in place, and I'm going to get some polynomial that the roots of that polynomial are going to be the eigenvalues of my matrix. So let's take 5 or so minutes with your team, maybe 10, to determine that characteristic polynomial. And then by looking at your answers to the first activity, the preview activity in 5.3, see if you can verify that the eigenvalues that you found in the previous preview activity actually are roots of this characteristic polynomial. So let's take 10 minutes to do that algebra with your team. So what you found when we first looked at this transformation, right, was that there was a direction of parallel stretching happening, that the vector 1, 1 was being stretched by a factor of 3 in the parallel direction, right? 1, 1 turned into 3, 3. And indeed, any other vector along that same line will also be being stretched by a factor of 3. Right? So that's the other thing, is that because when this equation has not unique solutions, it has infinitely many solutions. And so eigenvectors don't exist just in sort of singletons. They exist in entire infinitudes of solutions to ax equals lambda x. And those spaces are called eigenspaces. So sometimes it's easier to talk about eigenspace as being a single thing, and the eigenvectors are all the infinitely many vectors that lie within that eigenspace. But anyway, 1, 1 is an example of an eigenvector in the eigenspace, which is the line y equals x in this plane. And the stretch factor in that eigenspace is 3, because the length of this vector v is getting tripled by the action of the linear transformation. And so 3 is an eigenvalue with eigenvector 1, 1. But also -1 is an eigenvalue with eigenvector 1, minus 1. Because 1 minus 1 is getting exactly multiplied by -1 by this linear transformation reflected across the origin. And so when we find the characteristic equation of this matrix by subtracting lambdas on the diagonal and then computing the determinant, we end up getting the equation 1 minus lambda times 1 minus lambda minus 4 is equal to 0. And if we wanted to, if we didn't already know sort of what we expected the eigenvalues to be, we would multiply out that polynomial on the left-hand side. We'd get some quadratic, and then we'd use either factoring or the quadratic equation to solve it, right? And whichever direction that we went, we would figure out that 3 and -1 are exactly the two solutions of this polynomial equation, this characteristic equation. And so that is kind of the recipe, is if we want to find the eigenvalues of a matrix, I should just compute a minus lambda I by subtracting lambdas down the diagonal, and then take the determinant of that. Set that determinant equal to 0, and then try to solve the polynomial equation that you get. Right? And once you have the solutions of that polynomial equation, you can then go searching for the eigenvectors, for which that's the last thing that we'll talk about today in just a moment. For the cat example, there were 2 eigenvalues, 3 and -1, and each one of those eigenvalues looks like it had a one-dimensional eigenspace. Right? There's an entire line that's being vertically reflected. There's an entire line that's getting a parallel stretch. And so that might be explained by the fact that my quadratic equation split up into 2 factors, 3 and -1, and each one of those factors appears only once in the factorization of the quadratic that we would get on the left-hand side. But if I had a repeated root as a part of my polynomial algebra, that opens the door for some more interesting possibilities. And this is what was happening in our second example, 2, -1, 0, 2. So when we go looking for an eigenvalue here, we find out that it has an eigenvalue of 2 and an eigenspace of the x-axis. Right? Every vector on the x-axis is being stretched by a factor of 2. But that there was no other eigenvalue that we could find at all. So 2 ends up being a repeated root of the characteristic equation. And even though it appears twice as a factor of the characteristic polynomial, it actually doesn't give me a 2-dimensional eigenspace. It only gives me a 1-dimensional eigenspace. So we call this the deficient condition. We call the geometry that happens in that case a shearing geometry. So shearing is just like pushing a stack of papers over. It doesn't change the area or the volume of anything. It just kind of skews it. So skew is another word that's sometimes used to describe this kind of transformation, where we have a repeated root of the characteristic equation, but the dimension of the eigenspace doesn't match up with the multiplicity, the algebraic multiplicity of that repeated root. So that's the most complicated one to be searching for. the example of projection that we saw with, it was 2, -1, -4, 2, where the cat was flat, right? This was an example, and the reason that this happened is that one of my eigenvalues was 0. And the reason that one of my eigenvalues would be 0 is if the determinant of a minus lambda I equals 0 is true when lambda is 0. But if lambda is 0, that means the determinant of a is 0. And if the determinant of a is 0, that means my original matrix was not invertible. Right? So when my original matrix is not invertible, we know that it has at least one of its eigenvalues that's equal to 0. And if one of its eigenvalues is equal to 0, that must mean that we are projecting along some dimension, right? We can find some vector that's just getting sent to the 0 vector by this transformation. And here's such an example. And then the final example that we sort of looked at, 1 minus 1, 1, 1. This was an example where we have basically mostly, the most interesting part about the geometry here is that it seems to be mostly a rotation, right? That we can't find any parallel or anti-parallel examples where the image is either parallel or anti-parallel to the original. And so it would be interesting then to figure out what happens when we try to find the characteristic equation, characteristic polynomial for this particular matrix. So let's just do that real quick. So it's 1 minus lambda -1, and then 1 and 1 minus lambda. So there would be determinant of a minus lambda times the identity. I'm going to try to scroll up a little bit here. And so if I take this determinant, what I'm going to get is 1 minus lambda squared plus 1. Right? If I multiply that out. And then we're going to try to set that equal to 0. Well, what happens when I try to solve that polynomial equation for lambda, given that I have that plus 1 over on the left-hand side?
No real solution?
We're going to get no real solution because we're going to have 1 minus lambda quantity squared equal to -1. Right? And so if I want solutions of this thing, I'm going to have to use complex numbers. I have non-real solutions to this. In fact, if we wanted to do this real quickly, if I just take the square root of both sides,
you'll get I.
I'm going to get an I. So 1 minus lambda equals plus or minus I. And so then when I solve that for lambda, I'm going to subtract 1 from both sides and then multiply by -1 on both sides. So I'm going to get 1 plus or minus I are the two roots of this characteristic equation. And by the way, if you know about writing complex numbers using their polar coordinate representation, we could write this as the square root of 2 with an angle of 45 degrees. I'm going to write that as the polar coordinate representation of the complex number 1 plus and minus I. And so when we do that, we find out, hey, 45 degrees, that is the angle of rotation of my cat picture in this example.
X equal I, 1 plus I.
1 plus I, but 1 plus I and 1 minus I are both the solutions to this. And so actually, yeah, so square root of 2 angle 45 is 1 plus I. Square root of 2 angle minus 45 would be 1 minus I. But square root of 2 is telling me the scaling factor, how much bigger the cat picture is in the codomain compared to the original. And if we wanted to understand that, I suppose we would try to just stretch this vector so that it goes out to the end of my cat picture and see how long it is in the original. Yeah, it's square root of 2 times as long. So in an area, from the area perspective, the area of my cat is actually a factor of 2 larger in the codomain than it is in the original. And how could I have known that from my original matrix? What tells me from the original matrix how my area changes?
The determinant?
The determinant. And you can check that the determinant of 1 minus 1, 1, 1, that determinant is just equal to 2, in fact. So our classification of the geometry of linear transformations according to their eigenvalues is that there are these 5 cases, and these are the only 5 cases that can happen for a linear transformation. All of my positive real eigenvalues represent these stretches in a parallel fashion. My negative real eigenvalues are stretches with reflections over the origin. My 0 eigenvalues represent projections, squashes, places where I take a dimension and I just totally flatten it out. My non-real eigenvalues represent a rotation of some type. And my repeated roots give rise to the possibility of shearing as a geometric property of a linear transformation.